Good day, my angels. This is lesson 4, and this is really where we're going to put everything together. So we've been looking at Kirchhoff's laws for solving circuits. We have the voltage law, we have the current law, and then we have two main equations. We have Ohm's law, V equals I times R, and we have Joule's law, power equals V times I, and there was a few other ways to write each one of these, and I'll let you do that on your own. And so I've said to you, if I know any two of these things at any location in the circuit, I know all four of these things. We're going to talk now about circuits that are in series and in parallel. A series circuit is a circuit where resistors are connected in a row with no junctions between them. So which of these circuits, the first one or the second one, shows resistors in simple series? Absolutely this one here, because these three resistors have no junctions between them. This is not a series circuit because these two resistors have a junction between them, and these two resistors have a junction between them. So a series circuit, two resistors are in series if there's no junctions between them. Example 2 says, find an expression for the total resistance of a series circuit. There is a lovely proof, and I would normally in class go through it, but in the interests of time, I'm just going to give you the punchline to, well, you know what? I'll make up some numbers here. If this is 120 volts, and if this resistor here is 10 ohms, and if this resistor here is 15 ohms, and as if this resistor here is 20 ohms, and I said, solve this circuit, none of your strategies would work. You would say, well, start by labeling downhill. That's still doable. That's downhill. But then you would want to try and find total current. I cannot. There's no current anywhere. Then you would look for, knock, knock. Do I know two things? No, I don't. No, I don't. No, I don't. Then you might try and ski. I'm starting with 120 volts. I go through this resistor. I don't know how many volts that I lose. I go through this resistor. I don't know how many volts that I lose. I go through this resistor. I don't know how many volts that I lose. If all three of these resistors were identical, we could probably say they split the voltage evenly, 40, 40, 40, but they're not. So there is a step 5. And step 5 is, as a last resort, rewrite the circuit in its simplest mathematical form. So these three resistors are in parallel. What I'd like to do is rewrite this as one resistor, what I call R total, or just RT for short. And it turns out if resistors are in series, R total is just found by adding them up. In other words, if I rewrote this circuit as a single resistor, it would look like this. It would still have a 120 volt battery, but instead of 3 resistors, it would have one uber resistor of 10 plus 15 plus 20, which is 35, 45 ohms. Now I'm off to the races, because now I can find I total. I total is the total voltage divided by the total resistance. It's 120 divided by 45. $120 divided by 45. And I get 2.6 repeating. Amps. So what that means is leaving the battery is 2.6 repeating amps. And going through this resistor is 2.6 repeating amps. But in my original circuit, that also means I have 2.667 amps leaving the battery, which means going through this resistor, I have 2.67 amps. I have 2.67 amps going through that resistor, and I have 2.67 amps going through that resistor. And now, knock knock, I know two things. I can tell you how many volts I lose going through this resistor. It's going to be I times R. It's going to be 2.67 times 10. Brendan, you don't need your calculator for that. You can do it in your head. It's going to be 26.7, sorry, not 7 repeating, 6 repeating, 26.7 volts. I could also find out how many volts I lose through this resistor. It's going to be I times R. It's going to be I times R, 40 volts. And then I can also find out how many volts I lose going through this resistor. I could either, the bottom resistor, I could either go 120 divided by 45 times 20 and get 53.33, or I could have skied. I could have said I start with 120 volts, I lose 26.7, I lose 40, leaving how much? Well, if you go 120 volts minus 26.7, well, you know what? Let's even add some extra sig figs. Minus 40, you also get the same answer of 53.33 volts. So, having said all that, in the box on the next page, if resistors are in series, our total is add up the first one, add up the second one, add up the third one, add up the fourth one, add up the fifth one. Now that's if there's no junctions between those resistors. You can combine them as one Uber resistor just by adding them. So example 3 says, oh, by the way, also this is on your formula sheet. I used to make the kids memorize it, but I've mellowed out. Example 3 says, select the best answer for the voltage drop across the 20 ohm resistor. You know what? I'm going to solve this. So, step 1, label downhill. Step 2, try and find I total. I don't see I anywhere. Step 3, do I know two things? Do I know two things? No. Step 4, ski. Well, I know that these two voltage drops together are going to add to 100 volts. Step 5, the last step, rewrite the circuit in its simplest form as one resistor. Well, these two resistors are in series, and so really our total is 5 plus 20. It's 25 ohms. The circuit that they gave me is mathematically identical to a 100 volt source and a 25 ohm Uber resistor. And I'm just doing a quick sketch. You can see I'm doing a sloppy circuitry diagram. I'm not even bothering to put the zigzaggy resistor symbol in. This is just my rough work, but now I can tell you that I total is going to be V total over R total. It's going to be 100 over 25. Brendan, I can do that in my head. 4.0 amps. So that must mean that there's 4 amps going through this. First of all, 4 amps leaving the battery, but 4 amps going through the top resistor, 4 amps going through the bottom resistor, the right-hand resistor, sorry, and that must mean since V equals I times R, this must be using up 20 volts, and now I could go 100 minus 20, leaving 80, or I could go I times R. This must be using 80 volts. So the voltage drop across the 20 ohm resistor, more than 50 volts, and there's my proof. I actually solved it. Example 4, find the total resistance and current, and then find the current through and the voltage drop across each resistor. And we might even, just for giggles, find the power as well to let you know that we can find the wattage of each of these appliances or light bulbs or whatever they are. Step 1, label downhill. Step 2, try to find the total current leaving the battery. No current anywhere. Step 3, look for two things. I don't know two things. Step 4, ski. Well, starting with 100 volts, I would lose some voltage there, some there, and some there. These three are going to add to 100, but I don't know what each of them is. Step 5, rewrite the circuit in its simplest form as one voltage source and one resistor. These three are in series, so I can safely say that our total is going to be 15 plus 5 plus 5. I can do that in my head. It's going to be 25 ohms. I total is going to be I total is going to be 4 amps. So, leaving the battery, I have, 4 amps leaving the battery. Ooh, and that must mean I have 4 amps going through that resistor, 4 amps going through the right-hand resistor, and 4 amps going through this resistor. Oh, knock knock. I know 2 things. Then I know 4 things. So I can tell you that the voltage lost through this upper resistor is I times R, 4 times 15, which I'm pretty sure is 60 volts. The voltage lost through this right-hand resistor is I times R, 4 times 5, which I'm pretty sure is 20 volts. And then I could either ski and say 100 volts minus 60 leaves 40, minus 20 leaves 20, so this is going to be 20 volts right there. Or I could go I times R. Hey, the nice thing is I get the same answer 2 different ways. I must be right. 20 volts. That's series circuits. Now, what about a parallel circuit? A parallel circuit is where the resistors start and end at the same voltage or the same height. In my ski hill analogy, 2 resistors are in parallel if skiers can split up above them and meet up at the bottom at the same height, at the same voltage. So example 5 says, which circuit shows resistors in simple parallel? This one here. These 2 are in simple series with each other, and I could replace them mathematically as a single resistor and redraw this and turn it into a simple parallel resistor circuit. We'll do that later. Example 6 says, find an expression for the total resistance of a parallel circuit. Again, if we were in class, I would do a lovely proof, but I'm going to go straight to the punchline. Combining resistors in parallel, you can't. That's the short answer. What you can find is their reciprocal. So really what we have is this, 1 over R parallel. And I usually abbreviate R parallel as R and then 2 parallel lines, like we did back for forces. And that's going to be 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor plus 1 over the, whichever ones are in parallel with each other. Now you have to be careful. You can't stick any resistors that are in series in here. And we'll look at mixed resistor circuits next lesson. So I'd like you, if you have a calculator with you, please get it out, because I'd love to teach you a lovely, lovely, lovely shortcut. Example 7 says, find R total, I total, and then find V and I for all resistors. And I'm even going to say, let's find the power too, just for giggles. I'm going to, oh, no, I'm not going to zoom in because I need some room to show some work. So step 1 would be, remember, step 1 would be label downhill. Step 2 would be find the total current. Step 3, do I know 2 things? Step 4, ski, Kirchhoff's laws. Step 5, rewrite it. Hey, newsflash, we're going to have to rewrite this because I don't see current anywhere. I will label downhill. Downhill is that way, that way, that way, that way, that way. Well, I have to be honest, we could solve this without rewriting it, because we could say, you know what, Mr. Dueck? I can ski this run, and so I know that this is going to be 60 volts. And then, knock, knock, I know two things. Mr. Dueck, I could also ski this run. I start with 60 volts. I only go through one resistor. Whee! And that gets me down to the bottom. You know what, Mr. Dueck? I must lose 60 volts going through that resistor. And likewise, I could ski this run. I must lose 60 volts going through this resistor. So I got to be honest, I would not solve this by rewriting this, but what I'm going to show you is we can, and it will work. So, supposing I either didn't see that I could ski, or this was a more complicated circuit, I would like to rewrite this as one resistor. And so I would say those three resistors are in parallel. So 1 over R parallel is going to be 1 over 10 plus 1 over 15 plus 1 over 20. You can go like this. 1 divided by 10 plus 1 divided by 15 plus 1 divided by 20. That'll get you there. But all of you have a reciprocal button, a little x to the negative 1 button. Somewhere you either have an x to the negative 1 button or you have a 1 over x button. And one of the reasons your calculator has that is to make solving circuits easier. So here's what I would do, because I'm lazy. Instead of doing all that, I would go 10 reciprocal plus 15, take the reciprocal, plus 20, take the reciprocal. Now this is not the answer, this is the reciprocal of the answer, and so now I would hit my reciprocal button one more time. My calculator always automatically puts the answer button for me. That's the answer. Those three resistors in parallel, a 10 ohm, a 15 ohm, and a 20 ohm, can be replaced with a single 4.61538. Ohm resistor, which means I can rewrite this circuit as a 60 volt battery and a single 4.61538 ohm resistor. And that means I can find I total, which is going to be V total over R total. It's going to be 60 all over 4.61538. You know I'm going to use my answer button, right? 60 divided by answer button. Oh, that worked out lovely. Exactly 13 amps. So I'm going to have 13 amps leaving the battery. It's going to split up right here. Now, I can tell you what it's going to split up into because I could have gone 60 divided by 10, V over R, to get the current. It's going to be 6 amps. And I could tell you what it's going to split up into. It's going to be 60 divided by 15. So this is going to be 6 amps. This is going to be 4 amps. And I'll bet you this is going to be 3 amps. Hey, it is. If I go 60 divided by 20, V over R, that gives me the amperage. And so the fact that this works, I think, is a lovely proof that I can use this method. Oh, they also wanted me to find the power for all of the resistors. Okay, power equals V times I, so it's going to be 60 times 6. This is a 360 watt appliance. V times I, 60 times 4. This is going to be a 240 watt appliance. V times I, this is a 180 watt appliance. Probably none of those are light bulbs. Example 8. Find the voltage and power lost in each resistor, and then find the voltage of the battery. Okay. Step 1, label downhill. Step 2, find the total current. Hey, I know the total current. This question's going to fall apart. Step 3, look for 2 things. I don't know 2 things. I don't know 2 things. I don't know 2 things. Step 4, ski. Doesn't help much because I don't even know how high the chairlift is. Step 5, rewrite the circuit in its simplest form. So what I'm going to do, these two are in parallel. I'm going to write them as a single resistor. These two are in parallel. I'm going to write them as a single resistor. And these two are in parallel. I'm going to write them as a single resistor. In other words, I'm going to try drawing a circuit that looks kind of like this. I don't know the battery, but I'm going to have those two resistors right there. Those two resistors right there. And those two resistors right there as a single resistor. And why is that going to be so nice? Well, you'll see. So how will I combine? I'm going to erase my little highlighter now, if that's okay. How will I combine these two? Well, for those two, 1 over R parallel is going to be 1 over 10 plus 1 over 15. Don't forget, once you're done, to take the reciprocal of your final answer. A common mistake is kids go like this. They go, oh, okay, this is going to be 10 reciprocal plus 15 reciprocal, and they say, oh, our total is 0.16. No, that's the reciprocal of our total. Take the reciprocal of that. I can replace a 10 and a 15 that are in parallel with a single 6 ohm resistor. These two are in parallel with each other, so 1 over R parallel is going to be 1 over 20 plus 1 over 15. 20 reciprocal button plus 15 reciprocal button equals reciprocal of the answer. I think I typed that wrong. Did I type that wrong? It's not 15, it's 5. Jeez. Let's try that again. 20 reciprocal button plus 5 reciprocal button. Reciprocal, I think the answer is going to be 4. Yes, it is. This can be replaced with a 4 ohm, that's a terrible ohm symbol, resistor. These two, 1 over R parallel is 1 over 12 plus 1 over 12. I think that's going to work out to 6, because that's 2 over 12, which is 12 over 2. Oh, typed it wrong. 12 reciprocal, 12 reciprocal, reciprocal of the answer. Yep. So, now, those three mathematical equivalents, the 6, the 4, and the 6, are in series in this particular circuit that I've just drawn. So now I can tell you what our total is. Our total is just going to be 6 plus 4 plus 6, because if they're in series, I can just add them up. The total resistance of this circuit is 16 ohms, and the total current, they told me, is 5 amps. You know what that means? V total equals I total, R total. I can now tell you the total voltage. The total voltage is going to be 5 times 16, 80 volts. I'll go add that to my circuit up here. So I found the voltage of the battery. Now they want me to find each circuit. Now here's what I want you to notice. Remember, this circuit here is mathematically identical to this circuit here. So in this circuit here, I know that I have 5 amps going through there, 5 amps going through there, 5 amps going through there. Which means in this upper section, I must lose 30 volts, I times R. In this right-hand section, I must lose 20 volts, I times R. And in this bottom section, I must lose 30 volts, I times R. Also, I notice 30 plus 20 plus 30 gives me my 80-volt battery. So how many volts do I lose in this upper section? 30. How many volts do I lose in this upper section? 30. Now here's what that means. From here to here, no matter which path I take, I'm going to lose 30 volts. Each one of these, I lose 30 volts. 30 volts. Knock, knock. I know two things. I can tell you the current. The current is going to be V over R. The current in the top one is going to be 3 amps, and then I could either say, look, I have 5 amps coming in, 3 amps went along the top, 2 amps must have gone through the bottom section right here, or I could go 30 divided by 15, but no matter what, 2 amps. What about right here, this right-hand section? Well, no matter which path I take, I'm going to lose 20 volts. So I must have lost 20 volts in that resistor and 20 volts going through that resistor. Which means if I go V over R, this must be 1 amp, which means this has to be 4 amps. I did that by going 5, take away 1, or you could have gone 20. Let's make that a little neater. Divided by 5. Here, I got a few options. I could say, you know what? These are identical resistors. They're going to split the current 2.5 amps apiece because they're identical. But I also know that I'm going to lose 30 volts going through here and 30 volts going through here. Hey, is 30 divided by 12 2.5 amps? Yes, it is. Well, that's nice. Now they want me to find the power lost in each resistor. Power is V times I, so this is a 90 watt little appliance, probably a light bulb. V times I, this is a 60 watt little appliance. V times I, this is a 20 watt little appliance. V times I, this is an 80 watt little appliance. V times I, 30 times 2.5, I think is going to be 75. Hey, 75 watts, 75 watts. And that's how we can solve circuits by redrawing them. You get pretty quick at this after a while. So example 8 illustrates an important point, a really important point. The voltage drop across parallel resistors is the same as the voltage drop across the mathematical equivalent. The voltage drop through here had to be 30 volts, so each of these lost 30 volts. Through here had to be 20 volts, so each of these lost 20 volts. That's hugely useful. In a household circuit, plugs and lights are wired in parallel to 120 volts AC, and each circuit has a circuit breaker in the circuit. The circuit breaker is an automatic switch that will open when the circuit exceeds a set value, usually 15 amps. You have a couple of 30 amp lines, but the vast majority of your wiring is designed to trip at 15 amps. And when that switch is opened, it cuts off the current, and that way your house doesn't burn down. Example 9 says, if we connect a 1200 watt hairdryer and a 500 watt TV to the same circuit, will we cause the 15 amp breaker to trip? Really, it's asking find I total. Are we going to draw more than 15 amps? Let's sketch this as a circuit diagram. Now, the fancy symbol for AC is a circle with a little sine wave going through it like that to let you know that the current goes back and forth. So unlike the symbol for a cell or a battery, which is 2 horizontal lines or 2 parallel lines, one short, one long, AC circle, in fact, I couldn't get it to work. There should be a little there. Then it looks like I'm going to have a resistor right here. There's the hairdryer. And a resistor right there. There's the TV. I know that this is 120 volts, and they've told me that the hairdryer is 1,500 watts, and they've told me that the TV is 500 watts. Step 1, label downhill doesn't work for AC because the current is going back and forth, but let's pretend we're only looking at one specific section. Let's make downhill that way just so that we can follow in the same direction with our eyes. Step 2, find the total current. That's actually what we're going to want to find, so I can't do that. Step 3, do I know two things? No. Do I know two things? No. Step 4, ski. If I start here on my voltage source, I gain 120 volts. Whee! That gets me to the bottom of the circuit. How many volts must I lose going through the TV? I have to lose 120 volts. What about if I start going through the chairlift and go downhill this way? Whee! That also got me to the bottom. That means I must have lost in the TV. I must also have lost 120 volts. Knock, knock. I know two things. That means I know four things. Since they gave me power, I'm going to use power equals V times I. I'm going to find the current, which is going to be power divided by voltage. It's going to be 1500 divided by 120. 1500 divided by 120. Here I have 12.5 amps. In the TV, it's going to be power divided by voltage, 4.17 amps. When they combine, how many amps will I have when they combine? I total when they combine is going to be 12.5 plus 4.17 plus 12.5. Am I going to blow the breaker? Yep. This will blow the breaker. This will absolutely blow the breaker. Can't run this. Making sure I copy. Oh, you know what? I copied the numbers down wrong, didn't I? You're all screaming at me. This is supposed to be 1200, which means this is not 12.5 amps, which means this is not 12.5 amps. This is supposed to be 1200, Mr. Dueck. Geez, Dueck, learn to read. So this is going to be 10 amps, and so it's going to be 10 amps. You know what? It's going to be 14.17 amps. I'm not blowing the breaker after all, but I'm really close. If I plug anything else in, I'm going to blow the breaker. So the breaker will not trip. Barely. Sorry, folks. 1200 watts, not 1500 watts. My brain was bugging me. That's why I looked back. Something felt wonky. It seemed a little high wattage for a blow dryer. What's your homework? Going to give you lots of practice on this. So, number 1. Number 2. Number 3. In terms of the work that you show me, I would say when you show me how you've combined the resistors, show me how you found R total. If you want to find I total, V total over R total on your calculator and not show that line, I'm not going to freak out. But as soon as you find I total, label it coming from the battery. It makes your life much easier. Number 4 is good. 5 is good. 8 is good. I'll skip 7. 9 is good. So 9 is looking at number 8. If we add a resistor in parallel, or if we remove, or if we add, see what happens to the current. Will we trip the breaker or not? Something you should know because all of you, at least once in your life, will probably trip a breaker if you haven't done that already. 10 is good. 11 is good. 14 is good. And 15, here's an old provincial exam question. All right, I'll send out an answer key again on Wednesday. I'll try, let's see, the next lesson will come out on the May long weekend, probably on the Tuesday or on the Wednesday. Next week, Tuesday, so not this week, but next week after the May long weekend, Tuesday is a Pro D day. I'm not quite sure what that's going to look like. I don't think the district is just going to cancel it, but I'll probably send my lesson out then, either on the Tuesday or on the Wednesday. I don't think I'll send out my lesson on the Monday. I might, but there's a chance I might not have internet access. We'll see. Okay?